So in this class, we will discuss about plane stress and plane strain problems. Here, we have already discussed about three-dimensional stress system as well as three-dimensional strain system. So in that, to define clearly the stress at a point, we require 6 stress components as well as 6 strain components. Now that can be reduced in some cases. Three-dimensional problems can be reduced to two-dimensional problems in some practical cases. In that, you have two types. One is plane stress problem, another is plane strain problem. Now let us see what are the basic concepts of plane stress and plane strain problems. So if you take plane stress problems, in the case of plane stress problems, out of those 6 stress components, which are sigma x, sigma y, sigma z, they are the normal stress components. Tau xy, tau yz and tau zx, they are the shear stress components. Out of these 6 stress components, so you will be having only 3 stress components. That means it is reduced to 2 dimensional. So only sigma x, sigma y, tau xy exist. The other stress components will be 0. That means sigma z will be 0, tau xz will be 0, tau yz will be 0. So only you will be having this and this. So these 3 will not be there. So then not be there means they are neglected. Their value is very, very small. So that it can be neglected and the 3-dimensional problem can be reduced to 2-dimensional problem. So that means by generalizing Hooke's law, you can write the strain components like this. We have already derived it. So epsilon x is 1 by E into sigma x minus mu times sigma y plus sigma z. So here E is Young's modulus, mu is the Poisson's ratio. So in the case of the plane stress problem, we know that sigma z will be 0 or it can be neglected. So here this term will not be there. And similarly in epsilon y this term will not be there. In epsilon z this term will not be there. So if you simplify that, so epsilon x will be 1 by E into sigma x minus mu times sigma y. Epsilon y will be 1 by E into sigma y minus mu times sigma x. And epsilon z will be minus 1 by E. This minus goes to this outside you can take that mu. So minus mu by E into sigma x plus sigma y. So these are the simplified strain components in the case of the plane stress problem. The example for plane stress problem is a thin plate. That means the thickness is very small when you compare that with the length and the width. A thin plate subjected to biaxial stress. Biaxial stress means sigma x, sigma y and tau xy. This is a general example for plane stress problem where these 3 stress components will be 0 and only we have only sigma x, sigma y and tau xy. So this relationship between stress and strain in the case of a plane stress problem can be expressed in the form of a matrix equation like this. So this is a matrix equation. So you can always express set of equations in the form of matrices. So here in the LHS I am going to take the stress components as a column vector sigma x, sigma y, tau xy. If you equate them to strain components in the case of a plane stress problem, so a constant matrix will be there here, so which consists of only constants, that means E and mu terms, and then strain will be there. That means you can say that stress is directly proportional to strain. So if you remove that proportionality symbol and if you replace it by an equality symbol, you get a constant. Okay, k into epsilon. This constant is nothing but this matrix. In the form of matrix, you can write all these 3. So here, this is your sigma, this is your k, and this is your epsilon. So sigma is equal to some k into epsilon. So that k is this. So you have to remember this. That means if you want to write individually, so sigma x will be E by 1 minus mu square, which is common, into multiply these matrices like this. You know how to multiply the matrices. So 1 into epsilon x plus mu into epsilon y plus 0 into this. So you will be getting E by 1 minus mu square into epsilon x plus mu times epsilon y. Similarly, epsilon y will be E by 1 minus mu square into mu into epsilon x plus epsilon y. Of course, the third term becomes 0. 0, and tau xy will be e into 1 minus mu square into here 1 minus mu by 2 into gamma xy. That will come. These two will be 0. So if you still further simplify this, so I will write it separately. Sigma x will be e divided by 1 minus mu square into epsilon x plus mu times epsilon y. Sigma y will be e divided by 1 minus mu square into mu epsilon x plus epsilon y. So tau xy will be e divided by 1 minus mu square into 1 minus mu by 2. We can cancel this 1 minus mu with 1 minus mu here. This 1 minus mu square can be written as 1 plus mu into 1 minus mu. So that 1 minus mu get cancelled. It will left with e divided by 2 into 1 plus mu into gamma xy. And we know that e divided by 2 into 1 plus mu is nothing but g, rigidity modulus. So g into gamma xy. So these are the three constituent relations in the case of a plane stress problem. So which can be expressed as a matrix equation like this. So here normally we represent this as a column vector. So if it's only a single column, we represent like this. Here the sigma and epsilon, they are column vectors, and k is a constant matrix which is symmetric. Please note that this k is symmetric. That means rows and columns, they have the same elements. You can observe here. So this is about plane stress problem. Now we will discuss second type of problem, that is plane strain problem. So in the case of plane strain problem, among the 6 strain components, so you have 6 strain components like this: epsilon x, epsilon y, epsilon z, gamma xy, gamma yz, gamma zx. So these are the 6 strain components in a general 3-dimensional strain system. So in this, you will not be having this epsilon z, you will not be having gamma yz will not be there, gamma zx will not be there. That means any term connected with z will be 0 or can be neglected. So that means epsilon z is 0. That means epsilon z, according to the definition of epsilon z, it is dou w by dou z. Dou w by dou z, where u v w, they are the displacements along x, y, z directions. X, y, z, they are the coordinates of the point under consideration. So that means if you mean to say dou w by dou z is equal to 0 means this w is constant. That is the meaning. Okay. So similarly, this gamma yz is equal to 0. Gamma yz 0 means definition of gamma yz is it is dou v by dou z plus dou w by dou y. All these I have explained in the last lecture. You can go through that. And that will be 0 here. And gamma xz will also be 0. Gamma xz is dou u by dou z plus dou w by dou x, that is also 0. So these 3 strain components will be 0, and you will be left with only the other 3. So in the case of plane strain problems, you will be having only epsilon x, epsilon y, gamma x exist. The other 3 will be zeros. So this epsilon x is nothing but dou u by dou x, epsilon y is dou v by dou y, gamma xy is dou v by dou x plus dou u by dou y. How to write this? I have explained in the earlier lecture. Now, in this case, what happens with epsilon z? Let us see, here epsilon z is 0, so epsilon z is 0. According to generalized Hooke's law, which I have written here, epsilon z is 1 by e into sigma z minus mu times sigma x plus sigma y. So this will be 0 in the case of a plane strain problem. Since this is 0, this 1 by e cannot be 0. So what you can write is this will be 0. That means sigma z can be equated to mu times sigma x plus sigma y. Please note that very important difference you can see here. In the case of plane stress problem, sigma z is 0, but epsilon z is not 0. Please note, sigma z is 0, epsilon z is not 0. In the case of plane strain problem, epsilon z is 0, but sigma z is not 0. Be careful about it. So stress is there, but there is no strain. Now, example for plane strain problems is, you can give many examples here. Long cylinder subjected to internal pressure. So, for example, water is flowing in water supply pipes, you can say. So, you can see here, this is a long pipe. Along the length of the pipe, you take x direction. So, perpendicular to that y, another z. That means y and z, they are the diameter directions. X is the length direction. So, this is an example for plane strain problem. Another example is retaining wall. one length, one direction is having large dimension. That is the meaning. X direction in retaining wall also length is very large compared to your cross-sectional dimensions. Similarly, earthen dam, length of the dam is very very large compared to your height and width. Strip footing, this is also same. Strip footing, you have higher length compared to your width and depth of the footing. That means in any object, any problem in which case a structural element has larger dimension in one direction and smaller dimensions in the other two directions, that type of problem can be taken as a plane strain problem. So see the difference between plane stress example and plane strain example. Plane stress example, thin plane subjected to biaxial stress. Plane strain, these are the examples. So constituent relations, just like you have constituent relations in the case of plane stress, you have constituent relations in the case of plane strain also, stress strain relations. So once again I will write stress like this. So this is the stress vector and this is the constraint vector. So if you can express this in matrix form, this entire thing is your K now, and this will be your strain matrix or strain vector. So sigma is sigma x, sigma y, tau x, y. This K is this entire thing. And once again, you can see that this entire thing, this K is symmetric. So rows and columns, they have the same elements. First row, first column, second row, second column, third row, third column. They have the same elements and it is symmetric. So this is epsilon. That means we can express stress strain relations in the case of a plane strain problem using this relation. So sigma is equal to K into epsilon, where K is this. Please note that already we know one thing. This entire E divided by 1 plus mu, 1 minus 2 mu, we have used it as lambda. Earlier we have done one derivation, Lami's equations. So this lambda is called as the Lami's constant. So this can be written as Lami's constant. So Lami's constant depends on Poisson's ratio and Young's modulus, E and mu. So if you simplify this once again by multiplying, so this 1 minus mu into epsilon x plus mu into epsilon y into this will be equal to sigma x. Similarly, mu into epsilon x plus 1 minus mu into epsilon y plus 0 into this will be equal to sigma y. And this into gamma xy will be equal to tau xy. So this is how we can multiply these two matrices and we can get the values of these stresses. So please remember, these things are important. The constituent relations are important in both the plane stress and plane strain problems, and the equations are important, examples are important. So in the examination, they will ask you to distinguish between plane stress problems and plane strain problems with examples and constituent relations. So like that, they can give the question. So that means three-dimensional stress problem or strain problem can be transformed into two-dimensional stress or strain problem. So then such problems are called as either plane stress problem or plane strain problem. Okay. So next class we will discuss some more topics on these things.